Okay, so we're going to start chapter 9. And so we'll start in the beginning of 9:1. And now this chapter is, like I've been saying, very, very different than what we've been doing up to this point, although it does involve limits. But there's no integration at all in this chapter. This is all about sequences and series. Okay, now these are very important concepts, and we'll see how useful they can be as we go along. And a lot of what we're seeing here also overlaps to a certain degree with computer science, but no integration in this chapter. So, first of all, we need to start by introducing the concept of a sequence. So, a sequence is basically a set of numbers that have a specific index that tells us exactly what number they were associated with. So, formally, what you actually have is a function whose domain is the set of what are called the natural numbers or the positive integers. And the domain, so here's the domain. These are the some books use this fancy n to represent the natural numbers. Or sometimes they're called the counting numbers. For the obvious reason that these are the numbers that we use to count. In other words, it's the infinite set starting with 1, 2, 3, 4, 5, etc., etc. So in other words, you can think of it as the positive integers. So that's the domain of a sequence. A sequence is a function that maps us from the domain all the way down to infinity. And then the range is just the real numbers. Okay, in other words, anything can be in this range. Okay. Now, they make the point in the slides that in spite of the fact that a sequence is a function, it's not normally written that way. Usually what you have is this. You have a series of these terms. And then this would be pretty typical of A1, A2, A3, A4, up to infinity. So A is some variable. We don't know what that's equal to. The subscript is a member of the natural numbers. So these will be defined by a formula of some kind that will tell us how to calculate each of these terms based on the index. Okay, so in other words, we're going to have a formula of some kind that will say, listen, if let's say the index is 1, then you multiply it by 2 and then subtract 1 or something like that. It'll be a formula or a rule that tells us how to associate each of these indices with an actual real number. By the way, sometimes, I mean, it's not necessarily the case that they start at 1. It doesn't have to, although that's the most common way of expressing a sequence. But there are other ways of doing this. So so each of these terms, these are all called terms. Okay. And sometimes we write the sequence like this. We surrounded by braces, they're called. And that's a shorthand for saying it's A1, 2, 3, all the way up to AN. And yeah, and they're putting it out here too. Sometimes it's easier to start with 0. It depends on what we're trying to represent. But 1 is the most common starting point. Occasionally you do see 0. Very, very occasionally you might see negative indices, but that's kind of unusual. It's not impossible, but it's unusual. Normally we start at either 0 or 1. Much of the time we start with 1. Now, for the fun, just for the fun of it, they're going to give us some challenges here to figure out what exactly is going on here. In other words, here's a sequence. And let's take a look at it. They want to know, how did we get from one term to the next? Okay, so keep in mind, this is A1, A2, A3, A4, and A5. So the first thing we need to do is figure out what the pattern is. Now, clearly, in each case, the numerator is 1. We can think of this first term as 1 over 1. So in the numerator, we always have 1. And if you notice in the denominator, we keep doubling as we go along. So you can think of this as okay. So you could think of this sequence as 1, assuming that we start at 1, that is 1 over 2 to the I power. That way, starting with 1, you would know how to calculate every single one of these. Actually, I'm sorry, it's I minus 1, because the first one is 1, and that's going to leave us with 0. That's better. Okay, good. So in other words, when A1 equals 1 over 2 to the 1 minus 1, okay, A2 is 1 over 2 to the 2 minus 1. A3 is 1 over 2 to the 3 minus 1, 1/4, etc., etc. Okay, great. Now, how about this one? By the way, it's not necessarily always the case that the terms are determined by exponents. Other things can happen here too. In fact, we could have literally any pattern that we want. Now here, this one's a little trickier. And if you look at those numbers, you might remember this notion of the factorial operator, where we start with 0 factorial is 1, 1 factorial is 1, 2 factorial is 2 times 1, 3 factorial is 3 times 2 times 1, 4 factorial is 4 times 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1, 120. So the indices are 1, 2, 3, 4, and 5. Up here we have 2 factorial, 1 factorial. Oh, sorry. Well, this is in the denominator. Let me just write that a little bit. Well, it's fine. We'll leave it like this for now. So in other words, what's happening here is that you have, in each case, 1 over I factorial. So for A1, we have 1 over 1 factorial. For A2, 1 over 2 factorial. A3, 1 over 3 factorial. And you can see it works for all of them. Okay. All right, that was interesting. What about this one? Now, this one, it's a little unusual. Let's see what's happening here. So you've got, by the way, you should probably rewrite this first one as 10 over 1. So clearly 10 is always going to be in the numerator. Wow, this one's a little bit more challenging, isn't it? Because you can see what's happening. The differences are growing. Wow. So that's what the challenge here, because you start with the one and then it jumps up by two and then three and then four and then five. So um, you would start with I. Let's see. Um, and then to that you would add, oh, um, let's see. The first one is one. The second one is three. And that means you've added two. Let's see if that works. No, that didn't work. No, because it's two minus one. Oh, okay. So, okay, let's see what they've got. Oh my God. No, that's not it. That's right. That's not the right one. Um, Boy, that's interesting. But anyway, we do know that we keep adding the differences between them are increasing by one every time. So yeah, this is an interesting one. Sine minus sine. All right, well, we'll think about this one for a while, but the important thing is that we notice that the differences are increasing by one. This one, let's see. So remember, so the indices are one, two, three, four, five. It looks like this one is going to be I squared over I plus one squared. So that would make I1 be one over one plus one squared. Okay, that works. A2 would be two squared over two plus one squared. Oh, I think we're onto something here. A3, three squared over three plus one squared. Yeah, I think we're good. Okay, so this is the formula for this sequence. This one I still didn't figure out. We'll get back to that later on. And this last one, let's see what we have there. So indices are one, two, three, four, and five. So it looks like the numerator is just I plus two. Oh, no, it's not. It's let's try three plus Now it's always going to be adding two. Let's try this. So here you're always adding three. All right, let's try that. That's going to give me 3 plus 2 over 7 plus 3. Okay, so far, let's keep our fingers crossed. And that would leave us with, yeah, I think we got it. Okay, that's good. All right. So now here they're what they're going to do is give us the actual formula and then have us figure out what each one is, which is obviously a lot easier. So again, assuming that they want us to start with one, so 2, 4. Uh, so this one, yeah, this is going to be a very strange sequence. It's just going to keep alternating back and forth between 2 and 4. Yeah, you run into that sometimes. All right, how about this one? N over 1 minus 2n. So we'll start with 1. Okay, and then B3. What's interesting about these numbers is that they're actually getting smaller, in absolute terms, I mean. All right, well, anyway, that's those are the first four terms. 1, negative 2/3, negative 3/5, negative 4/7, et cetera, et cetera. All right, let's see what else they have for us. C, Cn. All right, so C1 will be 1 squared over 2. Ooh, this will be interesting. Okay, C cubed think I'll just copy this down here. A C3 rather is um, 9/7, et cetera, et cetera. Okay, great. Now, sometimes a sequence can be written in what's called a recursive form, which means each term is a function of previous terms. Which, by the way, reminds me, there's one sequence that you've run into, which actually is recursive, maybe without realizing it. You might remember the Fibonacci sequence from your travels. So what ends up happening here is, if you recall, is that you're basically taking for each term, except for the first two, um, each one is the sum of the previous two terms. So 2 is 1 plus 1, 3 is 1 plus 2, 5 is 2 plus 3, et cetera, et cetera. So this is considered to be a recursive sequence. And so you could define it as so there's once you start with 2, once you get to the second, I'm sorry, the third term, what am I saying? It's it should be 2. Once you get to the third term, which is 2, it's the sum of the previous two. And then once you get to that point, an, whatever it is n minus 1 would be the previous term, n minus 2 would be the previous two terms back. So it's recursive because no matter what n is, you're adding up the two previous terms. You're not adding a specific function of n, you're adding the terms themselves. Okay, so this is what we mean by a fairly complicated recursive sequence. And you know the history of this. It's a very interesting sequence, but this is an example of a recursive sequence. The one they have here, you have a sequence dn, and it's defined so that d1 is 25, that dn plus 1 is dn minus. So you're going to have, right, d2, let me write that a little clearer, will be 0. D3 would be -5, et cetera, et cetera. Oh, whoops, sorry. I wrote the wrong thing here. This is 20. That's 20. This is 15. That's a little bit more like it. This is 15, 10, and then it just keeps going down by 5 every time. Now, I mentioned this before, we're not going to be doing any integration in this chapter, but we still need to lean on limits. So the sequence itself can be converging to a specific value. Let me show you the classic example of this. Suppose you had something like this. So you basically have here a n equals 1 over n. No, not n. Does that look great? Yes, let's try that. A1 would be, no, that can't be right because that would be zero. Um, Actually, what we could do here is write it as a recursive sequence, where A1 is 1, and then after that, AN is, uh, oh, actually, maybe I have it there. Hold on. If that's it, then we have, nope, that's the same thing. It's going to go to zero. Try this. Oh, wait, I know what the problem is. Okay, I think we got it here. Oh, sorry, that's not supposed to be N. That's supposed to be an I. I think we're looking good now. Because A1 would be, okay, great. And then A2, 1.5. There we go. And then A3, yeah, this is it. All right. Anyway, so this is the sequence. It's not recursive. It's based on the individual indices. But what I wanted you to see is that the numbers are getting awfully small, aren't they? So you could easily imagine that in the limit, the sequence is converging to zero. Okay, the numbers are getting tinier and tinier. So if we apply limits to this case where the index, we're taking the limit of the index as it goes to infinity. And if we do that, it makes sense that this would go to zero. And if that happens, then we say that the sequence is convergent. On the other hand, remember we had one earlier where it just kept flipping back and forth between twos and fours. Yeah, this one. So this one is 2, 4, 2, 4, et cetera, et cetera. It's clearly not converging to anything. Okay, it's just going to, keep alternating back and forth. Here we say that the sequence is divergent. So what we would like to be able to do is figure out if our sequences are either convergent or divergent, and if they're convergent, what are they converging to? And the way we're going to do that is by using limits. All right, so By the way, here's an illustration of how this would work in general. You see how these points, which represent the terms of the sequence, as we get further and further along here, let's put that in here. Once we get past this capital M, all of the terms of our sequence are always within this interval. Sometimes they go up and sometimes they go down, but they never get further away from that middle line. They keep getting closer and closer to it. So this is a convergent sequence. And the limit Oh, I'm sorry, they're using ends here. Okay. All right. So that's what convergence actually represents. There's a limit. There's a limit for the sequence, and whatever it is, it exists, and therefore this sequence is said to be convergent. All right. So we can find some of these that are convergent. We can find some just by looking at them. It should be clear if they're convergent. Well, sometimes it's not always that obvious, but if they seem to be continuously getting larger or smaller, there's a real chance that they're convergent. Otherwise, they're probably divergent. All right. And also, they're going to use the slightly different notation here. Remember, because AN, which represents a sequence, is actually a function. We could write this concept in two different ways. The limit as x goes to infinity of this function is L, or the limit as n goes to infinity of AN is L. It means the same thing. All right, well, this is something we know and love. This is our old friend E. Um, if each term is 1 over 1 plus n to the n, the limit as x goes to infinity, as we remember from Calc 1, is E. So therefore, the limit of this is equal to E. So, like, if you just want to check it out for a minute, we can try a few of these terms. A1 would be A2 would be and what we expect to see. Now we know that E is approximately equal to 2.7128. So these numbers, well, so far we're looking pretty promising here. Whatever that is, 2.37. So you can see that what's happening here is that as we keep increasing n, we are getting closer and closer and closer. So this particular sequence is convergent with limit E. Okay. Now, sometimes though, um, we have divergent sequences because the limit is actually either positive or negative infinity. So if you had something like this, where clearly an is simply n squared, well, you can see this is not converging to anything. It's going to go to infinity. So we can have limits of sequences that go to infinity or negative infinity, which means that there's no limit. Now, here's some of the algebraic properties of sequences that we should know, and they look very similar to the properties of limits. And so you can see, for example, if I have a scalar multiple, I can just factor it out. Sum of our limits is the limit of the sums. The product is just the product, and the ratio is just a ratio, as long as we don't have division by zero. Here's a quick reminder what factorial looks like. We just saw that before. And now the squeeze theorem, if you remember, is the one where, say you have f of x, g of x, and there's some function in between that's always in between. That implies that the limits will be the same at any given point. Well, actually, no, that's not right because I didn't draw it the way I should have. They're supposed to, hold on one second. Let me fix this. They have to have this, the two outer functions have to have the same limit for this to work. Let me try that again. That's better. All right, here's g of x, and then here's h of x. Like I said, it's always in between. So right here, whatever that limit is, let's say that this is the 0.2 and this is the 0.4. That means for all three of them, we're guaranteed to have the same limit at that point. Okay, so we can sometimes put this to good use because we may have a couple of sequences and or there's a sequence that we don't really know what to do with it. But if we can show that it always is bounded by two other sequences, then it must have the same properties. Um, so like they want us to look at this one. Now, they just very conveniently happen to know two other sequences that form boundaries for this one. And so what they're recommended we do is show that because an and bn both converge to zero, then this one must also converge to zero too, because it's always in between the two. And so this is what it looks like in the graph. And by the way, it's okay if there's in the beginning, the middle function sometimes goes outside the two. As long as there's some point after which it always stays in between, then it will have the same limit. And here we can see that absolute value is not changing anything. These two both have a limit of zero. All right, now here we go. We have one where we're looking for a pattern. And it looks like the pattern here is 2 to the n minus 1 over 2 to the n. Fine. Ah, okay. So they want to know if it converges or diverges. Well, it's not immediately obvious just by looking at it. So what they're going to say is, listen, we know that we can take the limit of the corresponding function. To the x. Yeah, it's the same. It's we're just replacing the ends with x's. Okay, now because this is kind of a messy function, they want us to use L'Hopital's rule. And that means that what you're basically doing is, if you remember correctly, if just solving it directly gives us an indeterminate form, which means 0 over 0 or infinity over infinity, then you can replace this with f prime of x over g prime of x. And it kind of looks like that's what we're going to get here. So, so they did exactly that. They took the limit of the derivative and showed that the limit is in fact 0. And therefore, this must be a typo. Diverges means that it doesn't have a limit. Monotonic and bounded sequences. Now, sequences have different properties or can potentially have different properties. One of them is to be monotonic. And what that just means is that in this case, as you can see, each term is greater than or equal to the previous one, no exceptions. Okay. That means sometimes it's called monotonically increasing. Obviously, if it's the other way around, it would be called monotonically decreasing. Now, here's one that's clearly not monotonic because it goes up and down and up and down. That's the one with the 2 and the 4 that we had earlier. What about this one? Well, I mean, if you take a look at it, I mean, first thing you could do is just substitute some numbers and just look at them. Fourth order, that's enough. So it does appear that they're increasing each time we increase n. You can kind of see the reason why this is happening is because in the numerator, every time I increase n by 1, I'm increasing the numerator by 2, but I'm only adding 1 to the denominator. So the ratio of the two is growing because the numerator is growing more rapidly than the denominator. Or like what you could even do is draw a little graph. And you can see the numerator is clearly growing more rapidly than the denominator, which means the ratio must be growing and that will never change. Anyway, so this is what it looks like. So that means it's a monotonically increasing sequence. Okay, what about this one? Well, no, we're no such luck. You can see by the graph that this one goes up and it goes down, so it's not monotonic. Okay, now bounded means there is either a maximum value that the sequence can take on or a minimum value, or possibly both. So in other words, if there's some number that it will never reach, some number that's greater than all the terms in the sequence, we say the sequence is bounded above or bounded from above, and the number itself is called the upper bound. We also could potentially have a lower bound if there's some number below which the sequence will never fall. And if we're bounded from both sides, then we say the sequence is bounded. Now, this is where it starts to get very intense. The sequence can have more than one upper bound. So in other words, if there's, let's say that the sequence will never go above 5, that means that it also will never go above 6 or 7 or 8 or 9 or 10. So the relevant one that we need to know is the smallest of all those upper bounds, and we call that the least upper bound. And then it works the other way too. There's some lower bound. Let's say the lowest bound is 0, it's 0 is the lowest bound. But then that would mean so is -1, 2, 3, 4, et cetera, et cetera. In that case, what we're really interested in is what's called the greatest lower bound, the maximum of all those lower bounds. And then, according to this theorem, although they're not going to prove it, if the sequence is both bounded and monotonic, then it must converge it has a limit. Here's an example of that. 1 over n. Well, how large can it possibly get? Well, there's some limiting case. There's also some minimum amount, which is basically 0. And so you can also see that it's going to continuously get smaller as n goes up. So it is bounded and monotonic, which means it converges. As you can see in this case, it's 0. And then these two divergent sequences, this one is monotonic but not bounded. It'll increase forever. And this one is bounded. This one just alternates back and forth between plus and -1, by the way, but it's not monotonic. Okay, so in other words, it has a lower bound of -1. The upper bound is +1, but it's just alternating back and forth. So that means it's divergent. It does not have a limit. All right, so this one looks pretty straightforward. They're surprisingly simple because you're literally just plugging in the index into the formula. Just start with -11, and then when we go to 2, so this part is just going to cause the sign to alternate back and forth between 1 and negative and positive 1. So all we really need to focus on here is the denominator. And so in other words, this one will be And so -1 to the fifth power is negative. And so it'll just keep going on and on like that. Yeah, it's this one. All right. Now for this one, they want us to write a formula, which can be very, very tricky. So let's see. Well, it's not that simple as n plus 9, that's for sure. Or how about this? 9n plus 1. That would give me 10, 19. Yeah, all right. So I'm happy with my numerator. The denominator, looks like it's 9n plus 2. It's just always one more. What do you know? All right. Oh, those tricksters. Yeah, it would be this one. All right. So this is actually a very, very deep area of study. We're going to see some interesting results by the time we're done here. A lot of the functions that we know very well can actually be represented as a sequence. Now, here we're going to turn our attention to something related to sequences, which is a series. The difference between a sequence and a series is that with a series, you're adding up the terms of your sequence. So you're getting a number, or possibly infinity or negative infinity. So if an is an infinite sequence, then the corresponding infinite series, or just plain series, means add them all up. And if you notice, if you look carefully, n runs from 1 to infinity. Because the sequences themselves run, the index runs from 1 to infinity. So I just want to make sure you can see that. So it's an infinite sum is what we're looking at here. Now, these, when we only add up a finite number of terms, then we call those partial sums. All right, so the first term, the first two, the first three, et cetera, et cetera. If this sequence here that we're creating converges, then the series itself has to converge, and it has the sum indicated here. For example, here, I equals 1 to n, n equals 1 to infinity. The nth partial sum is the sum of the first n terms. If all of those possible sums converges to S, then the series itself converges. It gets closer and closer to a specific value. The limit S is sometimes called the sum of the series. On the other hand, if the sequence diverges, then so does the series. The series. All right, let's take a look at this one. So here's 1 over 2 to the n, and those are the terms. You can see they went through and calculated the partial sums, and they're able to take Sn, the general expression for Sn, and turn it into a formula. Okay, in other words, let's take a look at this. So let's say, and let's say we're interested in the fourth partial sum. That would be these four. That's going to be 15 over 16. Now, if I apply this formula, there you go. Okay, so we know that works. And if you take the limit, well, you can see what's going to happen. Use L'Hotel, you'll end up with 1. And that means what that's telling us is that if you keep adding more terms, you're going to get closer and closer to 1. And that's what it means for a series to converge. The sum is getting closer and closer to a specific constant. Well, that one's kind of challenging. By the way, this is a special case. If you notice, every other term cancels, these terms cancel, these cancel, and you're ultimately just left with the outer and the first and the last terms. So this one ends up being Sn equals 1 minus 1 over n plus 1. And again, if you took the limit as x goes to infinity, it's going to end up with 1. Because the limit of 1 over the x goes to 0. Now, that's an interesting one. It's just a bunch of ones. So the series itself can't ever converge because just the sum just keeps getting bigger and bigger and bigger as we add more terms, which is not what's happening, or not. That's what we mean by divergence. Yeah, so here formally, this has a name. It's called the telescoping series because all the intermediate terms cancel each other out, and all that's left is the first and the last terms in the series. Now, geometric series are different in the sense that um, what it means is that you're multiplying each of the terms by a constant ratio. So, in other words, a good example of this would be let's say that we have let's keep it simple. So you notice here that they started with 0. Okay, so that means here we have n equals 0, n equals 1, n equals 2. And there we're going to, in this case, have a equals 1. So the terms, according to this formula, should be okay. So in other words, just in simplest terms, a geometric sequence means, or series rather, that the terms are being multiplied by a constant. I mean, that's really the threshold, the thrust of it. Now, this is a particularly interesting one. Um, the one we're looking at now, it turns out that if r is an absolute value of r is less than one, this whole thing, this infinite sum is going to reduce to a over 1 minus r. And that's all there is to it. Interesting. Very interesting. We're gonna get some mileage out of that one. That's gonna come in very handy. All right, well, here's an example. They're gonna give us 3 over 2 to the n. So a is 3 and r is 1/2. So yeah, you can rewrite it like they did. And because r is less than 1, that means this entire sum is going to be 3 over 1 minus the half. 6. And that's all there is to it. Now you can see this graph they've given us. Um, that's the 6 right there. Now this one, on the other hand, is 3 halves. Okay, 3 halves to the n power. 3 halves is greater than 1. So that means you can see the numbers are just getting bigger and bigger and bigger. And so they will not converge. They will diverge. All right, so what about these algebraic properties? Well, they're pretty much what we saw earlier. You can factor out a constant. The sum of two series or infinite sums is the sum of the individual sums, and then the difference is just the difference. All right, so now they're going to give us a specific test to determine if a series converges or not, the nth term test. So I see that we're just about done here. So yeah, this looks like a good place to stop. We can pick this up next time with this nth term test for divergence. All right, so we'll stop here and we'll pick it up next time. Too. And remember, 9.1 is our introduction to sequences. And now 9.2, in 9.2, we switch our attention to series. And so what we've been doing here is looking at tests to find out if our series is divergent or convergent. Okay, if it's divergent, it doesn't converge to a specific sum. like diverges typically means that it goes to infinity or negative infinity. So there's several different tests that we can use depending on what information we have. So we usually try to pick the one that is the most straightforward to apply, but we also have to make sure that it is appropriate for each case that we're looking at. So here, for example, they're telling us right off the bat that if an infinite series adds up, or sorry, converges, then the limit as n approaches infinity of the term an equals zero. Okay, so in other words, what they're basically telling you is that if the terms are getting progressively smaller, then their sum will converge to some fixed constant. It will not be infinity. It will not be negative infinity. On the other hand, if the limit is not zero, that means that the series diverges, which means it does not have a limiting case. It either continues on to infinity or to negative infinity. So here's a couple of examples of this. So we start out with the infinite series, n equals 0 to infinity of 2 to the n. Okay. Just copy that into the notes. There we go. Now, clearly, with the exponent being n, if n keeps increasing, well, then what's going to happen is in the limit, we're just going to wind up with infinity. Okay. So that being the case, as the terms get larger and larger, and you can see what's happening here, the terms would be 2 to the 0, 2 to the 1, 2 to the second, 2 to the third. It should be pretty clear that the sum of these terms is not converging to a specific constant. The sum is just getting bigger and bigger and bigger. So we say here that the series diverges, okay? Meaning that it's just getting progressively larger, getting closer and closer to infinity. So this series diverges. Now, how about this one? This one's a little bit more challenging because they mixed in their factorial, but you may recall from Calc 1 that when you have a situation like this and we're trying to take a limit, we can go through and divide the numerator and the denominator by, in this case, n factorial. So that leaves us with 1 over 2 plus 1 over n factorial. Now, of course, n factorial grows very, very rapidly. So as we let n go to infinity, this goes to 0. So we're left with 1/2. So what that tells us is that the nth term, the limit of the nth term, is not 0. Okay, so since this is equal to zero, not 0, series diverges. So in other words, you have to imagine that the terms are getting smaller and smaller and smaller so that the sum is not growing without bound. It's just the numbers are getting smaller. And so the sums are getting closer and closer to a specific constant. That's when the series is said to converge. But here, that's not happening. So we say that the series diverges. Now, it turns out, interestingly enough, that when this limit is 0 with this test, which is what we're getting here, . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . So here the terms are going to be 1 over 1, 1 over 2, 1 over 3. And so this particular test, when the limit is 0, this test is inconclusive. So there's the test that we're applying here can't really be used to prove that the series is convergent. All we can do is either show that the series is divergent, or else we can show that the test is inconclusive and we have to try something else. So, it's not maybe as powerful as it could be, because, it would be nice if it could show divergence and convergence, but instead it can only be used to show whether a series is divergent. And if it's not necessarily divergent, we still have to try another test. So it's one of the many tests that are available to us. And so each one will have its own pros and cons. Okay, now here, anyway, we have this one. Now, in order to do this one, we have to go back a little ways and remind ourselves that when we were introduced to geometric series, this is a geometric series. As a quick reminder, and basically what you've got is a constant multiplied by r raised to a progressively larger exponent. And so you could have, for example, that would be considered, well, those would be the terms of a geometric sequence. And so the series would be 1 plus 1/2 plus a quarter plus an eighth plus a 16th, et cetera, et cetera. Okay. And so the idea here is that A is 1 and R is 1/2. So each time you go further along the sequence, you've got 1/2, 1/2 squared, 1/2 to the third, 1/2 to the fourth. So this is a geometric series. In the special case where R is in the absolute value strictly less than 1, we can reduce this to a very simple formula. This actually shows up quite often, with applications. It's very, very helpful. All right. You see this sometimes in finance, where we're trying to figure out, like interest rates and things like that. It's very helpful. Or in other words, you can think of it as like if we wanted to know how much money we would have in the bank after a very long period of time, we can use something like this. So anyway, as long as R is less than 1, and you can see why it can't be 1, because then you'd be dividing by 0. And it can't be greater than 1 because then you're dividing by a negative number. So it has to be strictly less than 1. And so then that means that this entire infinite series reduces to this very, very simple formula. So when you see an infinite series like this, the first thing you want to ask yourself is it geometric or not? And if so, does it have a ratio which is less than 1? If so, we're getting lucky, because that means it's easy to solve for the sum. So here you can see that the way this is written, A would be the 9 and R is 4/5, which is of course less than 1. So that implies the sum is equal to A, which is 9, 1 minus 4/5. And of course, that's equal to 9 over 1/5, which is 45. All right, so that's D. And now this one, it may not look like it at first glance. This is another case of a geometric series that converges. First, we rewrite it. Oh, actually, I forgot to label this. Hold on a second. Just so when you're looking at these notes, you can go back and find what you're looking for. This one is knowledge check number 1. And now the new one is, now let's check number two. And so based on the properties of the summation operator, we can rewrite this as and of course, the way it's written, you can rewrite it like this. Of course, it means the same thing. And now you can imagine each one of these is a geometric series. In this first case, A is 1, R is 1/6. In the second case, A is 1, and R is 1/7. In both cases, the R is strictly less than 1. So in the first case, we have A over 1 minus R equals 1 over 1 minus the sixth. And in the second case, we have A over 1 minus R. So this term is equal to 1 over 5/6, which is 6/5. Over here we have 1 over 6/7, which is 7/6. So remember, we're subtracting. So we end up ultimately with 6/5 minus 7/6. And of course, we need a common denominator. Let's choose 30. And our final result is 1 over 30. Okay, so, and there it is. Yes. All right, so that's the end of 9.2. Now 9.3 is going to introduce us to some more tests for series. Whoops, not that one. And so here we're going to introduce the integral test and define what we call a P series as well as a harmonic series. Okay. So now this integral test can be used to determine if a series converges or diverges. And then when we introduce the concept of P series and harmonic series, we're going to use that test to see if they converge or not. So how does this then work? Now notice that here our infinite series starts with 1. And well, assuming, now remember, we did say way back in the beginning that if you have a sequence like this, the terms A1, A2, A3, what you actually have here is a function where you're taking the natural numbers, the domain is the natural numbers, which is 1, 2, 3, 4, etc. And the range is all the real numbers. Some books use a special symbol for the real numbers. You see this like fancy R. Sometimes it's used to represent the real numbers. So then what they're saying here is that, assuming that that's the case, so in other words, each of these terms is actually f of n. So in other words, this does indeed represent a function. Then these two either both converge or they both diverge. Okay, because now remember too, an integral is nothing but an infinite sum. So these two things really represent the same results. You're still adding up an infinite number of terms, and in either case. So we're going to try this one. All right. So, in other words, we're treating this as f of x equals n over n squared plus 1. And so in order to use this test to see if the series diverges or not, we need to know, to use this test, that the function is positive, continuous, but decreasing. All right, so that's important. We have to make sure of this before we do anything else. Once we get out past one, in other words, not including the zero term, from one and on up to infinity, if the function is positive, continuous, and decreasing, then this is our result. So what they're going to have us do is this. We have to make sure. Um, Now, by the way, as long as, oh, you know what I just realized? I should make this x. Based on the way this is written, as long as x is strictly greater than 1, f of x is going to be positive. It can't be negative because of the way the function is defined. As long as we're restricting ourselves to x is at least 1. Okay, so that counts. Now, continuous, you can see that it's continuous. It's a rational function. And there's no value of x which would lead to division by 0 or any problems like that. So this function is continuous. The question is whether or not it is decreasing, because that's one of the requirements. Well, we can do one thing here. We can go to Symbol Lab and take a look at this. And then the other option is to simply take the first derivative and see what its sign is. So first, let's take a look at the graph. X over x squared plus 1. Okay, so it's x for x squared plus 1. And the graph is, oh, now keep in mind, they specifically told us to only focus on x greater than or equal to 1. So just by looking at this graph, it does appear, well, it's hard to be sure that that's 1. I mean, it's hard by looking, but it doesn't look like that is the case. From that point on, this function does appear to be continuously decreasing. But we can prove it by taking the first derivative and checking its sign. So we're going to need the quotient rule, of course. Let's quickly remind ourselves how that looks. All right, so that means we're going to have okay, so right now all we're interested in is the sign. Okay, so that means we have 1 minus x squared for x squared plus 1 squared. So the denominator is clearly positive, but as long as x is strictly greater than 1, or greater than or equal to 1, it should be clear that at x equals 1 itself, we're going to have 0. So that would be that the tangent line is flat. And then after that, this will be larger than this. And so that means the function will be negative. Okay. Right. So from here on, slope will be negative. Slope of the tangent line, that is. So that means we met all the requirements to use this test. So now we need to apply it. Okay. Um, yeah, so here we are. So what they're going to have us do is take the integral of the function, not the first derivative, but the function, the integral from 1 to infinity of x over x squared plus 1 dx. Of course, we can use substitution here. Let u be x squared plus 1. Then du dx is 2x. And then du is 2x dx. We don't have the 2, but we can supply it. Right? So then we have 1/2 integral du over u. All right, so by the first theorem of calculus, first fundamental theorem of calculus, I can rewrite this as, and oh my God, I almost blew it. You know what I just realized? We have to change the limits of an equation. Okay, let's do that right now. Right here, we're supposed to do that. So let's fix that. All right, so remember how this works. Once we change this to u's, remember we've defined u to be x squared plus 1. So when x equals 1, u equals 1 squared plus 1, which is 2. But at the same time, the 1x equals infinity, then u also equals infinity. So that means we have to rewrite this as 1/2 2 to infinity du over u. Now we're good. And of course, u is x squared plus 1. Well, the first one, now that means that you're evaluating it as all right. Now that still is infinity. Any way you look at it, it's still infinity. Okay, so you can add to infinity, you can subtract from it. So constants are irrelevant here. This is infinity. And that means, according to this test, the series diverges. So it seems like it's a lot of work. It's a lot of steps. But at least with this test, we can tell if it diverges or converges. So because this integral diverges, so must the series. If the integral converges, then so must the series. Now, P series, this is interesting. A P series takes the form um, n equals 1 to infinity of 1 over n over p, to the p power. Actually, let me just copy this. Oh, that's not. Yeah, that doesn't mean that sound never means anything good. I don't know what that is all about, but I'll just write it here myself. And oh, sorry, n equals one to infinity of one over n to the p power. P must be a positive constant. Okay, it's said to be a p series. So in other words, you're looking at something like this. Let's say, let's let p equals 2. Then you're going to have 1 over 1 squared plus 1 over 2 squared. Okay. Now, in the specific case where p equals 1, you'll have 1 over 1 plus 1/2 plus a third, because you're raising each one to the first power. Then, in that case, it's said to be a harmonic series. Okay, so if that exponent happens to be a 1, then it's a harmonic series. And furthermore, for this p series, we can tell whether it converges or diverges by the value of p. So p is between 0 and 1. Then we say that it diverges if it's greater than 1, then it converges. And you can see why, because if it isn't greater than 1, then the terms won't keep getting smaller, which is what we need for their sum to reach a specific value. So that's why p has to be greater than 1. We want those terms to keep getting smaller so that when we add them up, we eventually reach a specific constant. All right. So sometimes our strategy will be simply to see if we actually have a p series or a function of a p series, and then we can see if what the sign of p is. Like this one, 1 over n. Well, this is a p series with p equal to 1. There's an implicit 1 here. It doesn't say that, but there is an implicit 1, and that means that it diverges. And that's all you have to do. Wow. But on the other hand, this one we were just looking at a minute ago, this is a p series with p equals 2. And according to this rule here, because p is strictly greater than 1, the series converges. And then the what it converges to, the sum that this converges to would simply be the limit of this expression as n goes to infinity. Um, okay, so this is the natural log. Now, this one is different because they didn't, well, I don't think we saw this case. They just gave us 1 over n. I'm not sure where this comes from, unless the point of it is that yeah, I'll check into this separately, but I don't think that they've shown us how to do these. So we'll skip ahead to 9.4. All right. So here we're comparing series to each other. Sometimes we have series whose properties we already know, and we may be able to draw conclusions about other series from those. So we have the so-called direct comparison test, and we have the limit comparison test. And again, the whole point of this is to see if our series converges or diverges. Now, for the convergence tests developed so far, the terms have to be simple and the series must have special characteristics. A slight deviation might make these tests inapplicable. For example, we saw this one. This is a geometric series, but this one is not because of that n in the numerator. This is a p series, 1 over n cubed, where p equals 3, but the one on the right is not because of that extra 1 in the denominator. And then they're making the point here that this sequence on the left can be integrated. If we use U substitution, the one on the right would be a much bigger challenge. So here's the direct comparison test. Assuming that for all the terms in two sequences, A and B, as long as A is never greater than B, then if the larger of the two, the B's, converges, then A must also converge. On the other hand, if the smaller of the two diverges, then B must also diverge. So if we have a sequence that we're not so sure about, we can find another one with one of these properties and see if that will help us find whether we end up with convergence or divergence. So for example, here, now here's what they're going to do. They're going to say, well, listen, we know perfectly well, that we can't deal with this one directly. But what we can do is say, well, here we have another series which is similar to it and where we can make an important claim. So remember, so what they're telling us is that this sum, because of that extra 2 in the denominator, it must be true that 1 over 3 to the n must be greater than 1 over 2 plus 3 to the n. And in turn, be rewritten as and that should look awfully familiar. This is our geometric series. So that means we should be able to get 1 over 1 minus 1/3. So that means this series definitely converges. And we even know what it converges to. The sum is 3/2. Okay, so therefore, if now, and by the way, The larger of the two is the B. Okay. The way they wrote it here. This is the B. And so that implies that if the B converges, which is this one, then the A sequence or series, 1 over 2 plus 3 to the n, must also converge. Now, we don't necessarily know what it converges to, all right, but we do know that it converges, all right? So, and again, what they're saying here is that we started out with this 1 over 2 plus 3 to the n, which we don't know what to do with it, but we do know that 1 over 3 to the n does converge. In fact, specifically, it converges to 3 halves. And since we can show that the sum of the 1 over 3 to the n is always greater than 1 over 2 plus 3 to the n, that implies that because 1 over 3 to the n converges, that must also be true for this one. So, they're basically saying, listen, if you have a series which is very messy, we don't know what to do with it, maybe we can find another series whose properties we understand and use this relationship to determine if it is convergent or not. So here's the graphs of the two. And you can see they follow each other pretty closely, don't they? The limit comparison test. Sometimes a series closely resembles a P series or a geometric series, but the term-by-term comparison necessary to apply the test cannot be established. In other words, here it was very straightforward and obvious that this is true. No matter what the value of n is, we know this is true. But there might be cases where it's not so simple to establish that relationship. So instead, we have a workaround. We can try the so-called limit comparison test, which basically says that if for two sequences that all the terms are strictly positive, if the limit of the ratio converges to a constant L as n goes to infinity, then the two individual series, A and B, either both converge or they both diverge. All right, let's look at an example of this. Now, they mentioned this earlier. It may not look like it. This is a harmonic series. Remember, we saw, oh, this is section 9.3. Boy, I guess I put it away. Hold on. All right, here we go. Here's our harmonic series, but there's a formula here where they're telling us that it can have this form 1 over an plus b. So here, in other words, this is a special case of a harmonic series. This, in general, is also a harmonic series. So you can have not just something like this. The example we had here was n equals 1 to infinity, 1 over n. You could have, this is harmonic series. Instead, you could have, let's say, 1 over 2n plus 3 or something like that, and it would still qualify as a harmonic series. And then it would have the same properties as far as convergence and divergence are concerned. So here in their example, if, wait a minute. Yeah, here it is. So they're saying, well, here you go. Here's your general expression, assuming that A and B are both strictly positive, and we're going to compare these two, which we know is a harmonic series from 9 by 3. And we also know that the harmonic series diverges because P, there's an implicit P there. P is the exponent, which is 1 in this case. Okay, so let's take a look at this. All right, so now this more general expression, we can take its limit. And so what they're doing here is this. Taking the limit, but they're dividing. Looks like they're dividing out by, oh no, I'm sorry. I know what they're doing. I forgot. You know what they're doing? They're taking the two that they're trying to compare to. They're not trying to take the limit and divide out, the largest term. What they're doing here is this. They're treating 1 over an plus b as this an in this expression. Okay. So in this expression, the general expression for a harmonic series is our A. And then B is the 1 over n. Okay, this one. Okay. And then they're going to show us that algebraically, this is equivalent to because divided by 1 over n is the same thing as multiplying by n over 1. And because that's infinity, what we can do now is divide out the n's. This goes to 0. So we're left with 1 over n. And since this is guaranteed to be positive, that means that this case diverges. Okay. So yeah, then they're going to give us a, now you can see that like the ones on the right are the ones that we already know to be P series. Um, we know what their properties are. The ones on the left are the challenging ones, but if we can compare these directly to each other and show that term by term one is greater than the other, we can use this test. And we'll end up being able to conclude that these three messy ones on the left, in the first one converges because the one on the right converges. The one on the left down here, number two, they both diverge. This one diverges, so does this one. And then, of course, we know that this one converges because it's a P series with a power of three. And that means this one also must converge. Now, this is interesting. It's saying disregarding all but the highest powers. Um, so in other words, I guess what they want us to do is simplify it. I'm not sure why they would say that, but so you can reduce this to and then oh, I see what they mean. They want us to, I see. They're having us compare this with this. Okay. So then the limit turns into one. That means that the series converges. Okay. Yeah, you can see. So what they do is they rearranged it algebraically, and they ended up with n squared over n squared plus one, which means that what they would have done is divided. This would have been reduced to the limit as n goes to infinity of one over one plus. Wait a minute. I missed something. No, n squared. Sorry, one plus one over n squared. This goes to zero, so we end up with just one. Ah, okay. Let's see what comes up in section 5.